Hello everyone, this is Yulai, a PhD student from Huazhong University of Science and Technology. Today I'm going to present our work, SAVE. SAVE is a learning enhanced index that filters data in modern data analytics services by capturing data patterns. Here, you see a typical data analytics services deployment. In such deployment, data is often persisted in remote cloud storage, such as Amazon Symbol Storage, and accessed by computer nodes during query execution. Typically, these services organize data records into compressed blocks, which is the smallest unit of file from remote storage. The increasingly larger volumes of data and disaggregated storage make data access a major cost for query execution. To enhance query efficiency, these services usually maintain lightweight per block metadata to skip blocks. The most common form of per block metadata is zone map, which stores each column's minimum and maximum value in a block. As shown, the zone map for the fourth block shows that the block contains data ranging from 100 to 200. Consequently, for the query filters for records with a value of 80, the block 4 can be skipped. Although zone maps are very cost-effective, their filter performance is highly dependent on the data layout. For unordered attributes, which are common in cloud database, zone maps may produce a large amount of irrelevant data reads, which we call false positives. B-plus trees are effective indexing structures to address the problem of zone maps. To skip blocks, the leaf nodes of a B-plus tree store individual keys and the pointers to blocks containing it. Such a fine-grained structure allows B-plus trees to achieve no false positives, but cause non-ignorable storage overhead on large volumes of cloud data. To mitigate the storage overhead of traditional B-plus trees, many compression methods have been proposed, such as prefix and suffix truncation and node compression approaches. Among these methods, learned indexes have shown the potential to dramatically reduce storage overhead by replacing tree structures with linear function models. However, there is an issue. In data analytics, all individual key block pairs still need to be maintained, resulting in a significant storage cost. Throughout this presentation, you will see that we tackle this issue by proposing an index SAVE that groups keys based on data patterns. The key insight behind SAVE is that there are patterns in real-world data, making neighboring keys show similar trends in block distribution. To show block distribution, we sort keys of the indexed column and map each key to blocks containing it, similar to a fully inverted B-plus tree. Here, two examples are presented. The left one is from the Wikipedia dataset. Each block in the dataset is a log file that records page view statistics. The view count column represents the number of visits to a web page. As shown, small view counts are distributed in almost all the blocks, since pages with low visits are very common. Conversely, larger view counts are confined to different time blocks due to emerging hot topics. Another example is from water level monitors, showing how the water level changes in different monitoring stations. Since the water level is affected by the seasons, the changes also follow a pattern. Usually, the water level of most stations does not change much. But during the flood season, a few stations may monitor great changes, and such uncommon changes occur at the different blocks. Leveraging these patterns, SAVE groups key ranges with similar block distribution into a single region to optimize the storage cost. Now, I will give you an intuition of how SAVE groups keys step by step based on the patterns in Wikipedia dataset. The first step is sorting. Similar to a B+ tree index, Sieve sorts each individual keys on the leaf nodes, and associates each key with blocks containing it to show block distribution. The second step is partitioning. Sieve groups contiguous keys mapped to the same blocks into a single partition. As shown, keys 31 to 36 exist in the same block set and are grouped into a broad partition P1. However, keys 1001 to 1006 tend to appear in different blocks, and thus are organized into multiple narrow partitions. By storing information about a partition rather than individual keys, the storage space is saved. The third step is segmenting. To further reduce storage requirements, Sieve merges partitions that arise from different block sites by tolerating minor false positives. As shown, Sieve normalizes narrow partitions P2, P3, P4 to be equal size and groups them into a single segment. While this process will introduce false positives, for example, when answering the query will count equals 1005, it significantly reduces the storage overhead. More specifically, since partitions in a segment are equal size, Sieve does not need to store the ranges of each partition. Instead, it only needs to store the start key, end key, and the partition size of the segment to locate partitions. However, here comes the problem: how to identify the key-space regions that can be organized into partitions and segments with minimal false positives. To handle this issue, Sieve leverages a cumulative distribution function to model the trends in block distribution. As shown, when there is a difference between the block sites mapped by contiguous keys, for example, keys 1002 and 1003, the value of the function increases by 1. This function models the frequency of changes to mapped blocks, which can be used to find the best suited partitions and segments. More specifically, we approximate the CDF model with piecewise linear functions, and the key space is divided into several segments. There are two benefits of this fitting process. First, the trends of block distribution can be captured by these approximated functions, and the linearity of a function implies that its key space is exactly a segment that can be divided into equal-sized partitions with fewer false positives. Next, the y-axis value of the linear segment represents how many changes appear, indicating the number of partitions should be generated. In this example, there are two changes in the key space 1001 to 1006, and thus the segment should be divided into 3 partitions. If you are interested in the theoretical analysis of the relationship between false positives and the approximated functions, please refer to our paper. Moreover, system users usually want to set a storage budget for indexes. Therefore, we propose a simple heuristic to control the index size where avoid false positives as much as possible. As shown, we classify segments into 2 types based on the storage budget and the partition size given by linear functions. Intuitively, larger partition size result in fewer partitions, making the storage budget tend not to be violated. Therefore, we label such segments as inexpensive and assign partitions to them directly based on the approximated functions, such as segment 1 in the example. On the contrary, for expensive segments with a small partition size, we use a heuristic score to evaluate them. Intuitively, expensive segments with a larger size and number of blocks may cause more false positives. Therefore, the score for the expensive segments are calculated based on these two metrics, and the remaining partitions are assigned accordingly. As shown, since segment 2 contains more blocks, more partitions are assigned to it. By limiting the number of partitions in this way, SIEV is able to limit its size while avoiding large false positives. Now in the paper, there are various other design aspects we explore. We show how SIEV performs lookup operations for both point and range queries. Additionally, we present a highly efficient insert strategy designed to reduce the insertion overhead while managing false positives. We conduct an analysis of the limitations of our approach, considering factors like sparse data and underlying block distribution. Furthermore, we present cost models to theoretically analyze the false positive rates and search time complexity of SIEV. Here, you see the evaluation of SIEV on 3 real-world datasets. According to the proportion of missing keys, the datasets are classified into 2 categories: dense data and sparse data. Among them, Wiki and Maps are sparse datasets, while Star Sales is a dense dataset. To ease the comparisons, we generate 3 SIEVs of different sizes by controlling the storage budget. First, I will give you the size of these indexes. On the y-axis, you see the size of each index, which is normalized with the indexed column size. As shown, SIEV.1 and fingerprint, a lightweight per block metadata, show low storage overhead across datasets. The size of SIEV10 is much larger than SIEV.1, but still achieves up to 90% reduction the Cuckoo index, which is a recently announced set member filter. Fate is a learning index and achieves no false positives at the expense of maintaining all the key block pairs. Then you can see the filter performance of all the above methods across datasets and selectivities. For each selectivity, we randomly generate hundreds of queries and show the average results. The y-axis represents the scan ratio, the fraction of blocks accessed of the total number of blocks. The smaller, the better. As shown, SIEV performs better on dense dataset Star Sales, since sparse data causes gaps in the key space, forcing SIEV to either allocate more space to capture the gaps or tolerate more false positives. Moreover, the performance of SIEV improves as the selectivity and storage budget increase. On point queries, SIEV is able to achieve comparable performance with Cuckoo index, while reducing storage overhead by up to more than 90%. On range queries, we can see that SIEV reduces data access by up to 80% at smallest size, compared to the best counterparts. Now, you can see the filter performance of SIEV with different block sizes. It is evident that larger block sizes lead to worse filter performance for all data skipping methods. Specifically, as the block size increases from 10,000 to 200,000, the scan ratio of SIEV increases by up to 21%. Finally, you see the initialization time of SIEV on 3 datasets. The major cost in SIEV's initializations is to scan the records and build a sorted array of key block pairs, which is shown in shadows. Thanks to the efficient segmentation algorithm, SIEV is still able to achieve comparable performance to most counterparts. In this talk, we introduce SIEV, a novel index designed to optimize data skipping for modern data analytics services. Unlike existing solutions, SIEV groups contiguous keys into partitions and segments, effectively reducing storage costs. Moreover, by capturing patterns in block distribution, SIEV is able to balance storage overhead and false positives caused by the grouping process. That's the end of talk. Thank you for listening.